Hi again. So in this lesson, we're going to look at a hypothesis test for a single mean. And we're going to use the theoretical method and the simulated method. Okay, so let's look at our example here. A tire manufacturer is considering a newly designed tread pattern for its all-weather tires. Tests have indicated that these tires will provide better gas mileage and longer tread life. The last remaining test is for braking effectiveness. The company hopes the tread pattern will allow a car traveling at 60 miles per hour to come to a complete stop within an average of 125 feet after the brakes are applied. Okay. They will adopt the new tread pattern unless there's strong evidence that the tires do not meet this objective. The distances in feet for 10 stops on a test track are shown in the table to the right. Okay, so I'm going to underline some stuff here. They want to stop within an average of 125 feet. They will adopt the new tread pattern unless there is strong evidence that the tires do not meet this objective. Okay, so this is a really interesting way to word it, right? They could want strong evidence that the average does meet the objective, but that's not what they're doing. They're saying unless there's strong evidence that they do not. Okay, so you could think about what the difference between those two tests would be. And we have our data to the right, stopping distance in feet. Okay, what are we going to be doing here? You are the statistical analysis team hired by the company. What hypotheses and level of significance would you use? Test those hypotheses, state your conclusion. Verify this with a corresponding confidence interval. Would you recommend this company adopt the new tread pattern? Why or why not? Okay, so we're going to start with our hypotheses and then level of significance. Okay, so if you want to try this out on your own, feel free to pause and try it out and then come back and double check. So first we're going to write the hypotheses. So our null is going to be that the mean, or mu, is equal to 125 feet. Okay, right, so that's the value, that's kind of the cutoff value. We're going to assume that it is an average of 125 feet. Now the claim, the alternate, which way are we going to go on this one? They're saying they're looking for strong evidence that the tires do not meet this objective. So I'm going to use mu greater than 125 feet. And so essentially I'm saying the alternate is the tires don't meet the objective. Okay, different test than if we were testing that they strong evidence that they do, right? Then that would be less than 125 feet, okay? Okay, let's move this up here. What would a type 1 and type 2 error be in this context? Which has worse consequences? Use this to set your significance level, okay? Right, so remember, in order to set our significance level, we want to compare the type 1 and type 2 errors and see which one is worse, so we get some practice with that. So let's do a type 1. Type 1 error, and my method, if you like the way I do it, I always think of the null as the negative, meaning you don't have whatever, and the alternate as the positive. That allows me to use my false negative and false positive. So type 1 error is a false positive. And so I essentially state this, but it's not really true, okay? So we conclude the alternate. We conclude the tires don't meet the objective. But they really do. Okay, so that is one type of error that could happen. Let's look at the type 2. that is the false negative. So that would be, we conclude that they do meet the objective, but they really don't. We conclude the tires do, it's also the just the opposite of the first one, which is kind of nice, do meet the objective, but they really don't. Okay, so take a look at these two error types. Which one do you think is worse? We conclude the tires don't meet the objective, but they really do. So that could be a problem for the company where they don't use the tires that they really could have used. Or we conclude the tires do meet the objective, but they really don't. That is more of a safety issue, right? So then they might adopt these tires, but they really don't meet the braking distance. So I think type 2 is worse in this case. Is worse because of safety. Right, so essentially in this case, unsafe tires would be on the road. Okay, and now it's been a little while since we've done this, but do you remember how we set our alpha because of that? So when type 2 is worse, we make alpha bigger, and usually 0.10, okay? So when type 1 is worse, we make alpha smaller. When type 2 is worse, we make alpha bigger. Okay. Great. One more question here. When would we use simulation versus a theoretical test in real life? Okay, so we've got this situation here, and let's kind of put ourselves in this situation of a statistical analyst. Would we do the theoretical or would we do the simulation? Or both, okay? So we can use simulation anytime as long as the simulation matches the real life situation, okay? But we can only use a theoretical test if our conditions are met. Okay, so that's kind of the trade-off. You can use simulation in more cases sometimes. We can use simulation anytime as long as the simulation matches the real-world situation. You know, like we've looked at flipping coins before, doing a 50-50 kind of thing. We have to be able to have a simulation process that matches that whatever kind of probability is going on. Okay, and luckily we have a lot of tools to do that now. We can only use a theoretical test when the conditions are met. Okay, so let's go ahead and look at the conditions. A lot of times I do simulation first, but let's go ahead and look at the conditions first this time and see if we could do a theoretical test, and then also we'll follow it up with a simulation. Okay, so I'm going to switch to the next page. Let's go through the steps for a theoretical hypothesis test for a single mean. Okay, and we're continuing the case that the population standard deviation is not known. So I'll put sigma unknown, and in that case we use the t-distribution, okay? And I guess I wrote it right there too. So this is a t-test of a mean. So just like you're used to, we're going to write the null and alternate hypotheses, check the conditions, write the observed statistic, which is x bar, and calculate our test statistic. So here's our test statistic formula. And you'll remember from last time when we reviewed the sampling distribution that the standard error is s over square root of n. Okay, so this is essentially it's like a z-score, but now it's a t-score. We're taking our mean minus the null value. How far from the null value are we? And then how many standard errors away is that? Okay, so same idea as the z statistic, but we're using the t-distribution. So we'll use the t-distribution calculator with degrees of freedom n minus 1 to find the p-value. And the last two steps are just like you're used to. Compare the p-value with the significance level, determine whether the result is statistically significant, state the conclusion in context, including the p-value and the decision. Okay, so let's just review our conditions. These will be the same as we just looked at for the confidence interval for a mean. Independence. The individuals or subjects must be independent of each other regarding the variable measured. Okay, we need a random sample, randomization. Large population. If sampling without replacement, we must be sampling from a large enough population to consider the individuals independent of each other. So sometimes it's called the 10% condition, or the population must be at least 10 times our sample size. That's usually how I write it. Okay, and then sample size. Either if we know our population is normal, then any sample size is fine, or we check that our sample is nearly normal, or we have a sample size greater than or equal to 30. Okay, so 3 different ways to check this one out. If there are outliers or a strong skew, we cannot use this method. So we will be checking the histogram and box plot unless we have 30 or more. Okay, so let's write out the conditions for this situation. Okay, independence. So, oops, there's no dot there. So this is an interesting situation. It's not a survey, right? It's a measurement. So this is coming from, these are stopping distances in feet. So essentially there are some different trials here, right? So they're testing these tires on a car or on multiple cars, and they are measuring the stopping distance. 10 stops on a test track. Okay, so these are individual trials, right? So I'm going to call them the stopping trials. The stopping trials must be independent of each other in terms of the variable we're doing, so in terms of stopping distance. Okay, so what are some things we might want to consider there? Right, we should consider this as we're setting up this experiment before we even take the data, right? We consider these conditions so they'll be met. Maybe is the weather, is there something with weather, or are we doing single or multiple cars? The temperature, is it like, are they starting in the morning and going into the afternoon? So there's a big temperature variation. Condition of the brakes, like if it's the same car, are the brakes wearing, and that would affect the test. So lots of different things to consider in kind of an experiment like this. So I'll list some of these. Oh, also maybe the driver, right? Is it the same driver or different drivers? Driver, weather, same car? I don't know. Temperature, brake or tire wear. Okay, so any of those things we might want to double check. Okay, and then randomization. Okay, so this is a different kind of situation, right? This is more of an experiment versus a selecting parts on an assembly line or doing a survey or something like that, right? So this is an experiment, so this doesn't really, I don't think this really applies here. This is an experiment. Rather than a random sample. Okay, so we do want to consider all these other factors and like the, type of car, size of the car, all those kind of things seem really important. Okay, next one is large population. You might also be figuring out that this one also does not apply because large population is only when you're sampling without replacement. This is a trial situation, so we're not sampling. We're not sampling without replacement. So this does not apply. Okay, last one, sample size. This will apply. Okay, let's check our N. So I believe our N is 10 stops. So N equals 10, so it's not 30. We could think about, do we know that our population would be normal? I don't really know what shape that would be. So let's check that our sample is nearly normal. Okay, great. So I will get the data and plug that in. We'll check nearly normal and continue our test in the next video. So see you there.